Now we are discussing about gradient checking. We have calculated the dou j by dou w and dou j by dou b, but we want to check whether our calculation is correct or not. For that we use the gradient checking. How we will use, that's we are going to discuss now. This is a curve theta cube. On the x-axis theta, on the y-axis we are taking it as a f. So f of theta is equal to theta cube. By using the calculus, we know the differentiation for this is 3 theta square. But when we want to find the differentiation by using the numerical computation method, we take that point at theta, we are taking the value of f, and we are taking nearby 2 points. This is theta plus epsilon, at theta plus epsilon f value, at theta minus epsilon f value. And we believe that these 2 points, when we join these 2 points which are near to this theta, when we join these 2 points, this forms a straight line. Because we have taken only a very near values, we are taking a very near values, it is forming a straight line. From our previous knowledge, we know that whenever we are taking a circle, when we join very nearby points, 2 points, this is almost behaving like a straight line. We are using that concept. Now we have taken 2 nearby points. One is theta plus epsilon and the second one is theta minus epsilon. Because these two, when we join these 2 points, it is forming a straight line. We want to find out the slope of this straight line. How to find the slope of this straight line? By taking the y2 minus y1 and x2 minus x1. What is the y2 minus y1? Here I am taking the theta plus epsilon as x2 and theta minus epsilon as x1. Then f of theta plus epsilon is y2, f of theta minus epsilon is y1. Now y2 minus y1, x2 minus x1 is nothing but f of theta plus epsilon minus f of theta minus epsilon by 2 epsilon. This is what we are calling as differentiation of f of theta, or differentiation of f with respect to theta. Means whenever we are changing the theta, what is the value of f that is changing? We are substituting theta plus epsilon 1.01 whole cube. We are substituting theta minus epsilon, that is 0.99 whole cube. Epsilon is a very small value, that is 0.01. When we are dividing it with 2 epsilon, it is giving 3.001. By using our normal calculus, the differentiation for theta cube is 3 theta square, and because we are taking this differentiation at theta equal to 1, the result is 3.001 and 3, almost they are equal. So our numerical computation approach now checked the calculus method, we have differentiated the function f of theta. There is another way, there is another approach that's already we study from the childhood onwards, or whenever we want to differentiate, that is limit. Okay, we will progress and we will discuss. This is a limit epsilon tends to 0, means epsilon is very small value, f of theta plus epsilon minus f of theta minus epsilon by 2 epsilon. This is f differentiation of f of theta. Means whenever we are changing the theta, how the value of f is changing. There is another notation, that is f of theta plus epsilon minus f of theta by epsilon. We can use the right side method or left side method. But when we are using the left side method, the error is in the order of epsilon square. Epsilon square means it is 0.0001. When we use the right side method, the error is in the order of epsilon, means 0.001. So when we calculate by using this method, the output is 3.03. So error is 0.03. That's why to minimize the error, we are choosing the left side method. But in neural network, we are having many parameters. We are having many layers, and depending upon the layers, we are having many parameter matrices. We are reshaping all these parameter matrices. We are reshaping the elements in all these parameter matrices into a single column matrix. We are calling that as a vector theta. And similarly, we are taking the dw1, db1, dw2, db2, and we are reshaping all those dw's into a single vector or single column matrix, and we are calling that as a d theta. Now, we are calculating the differentiation by using the numerical computation method just now we have discussed. In this method, as we already have the matrix theta and d theta, now we are changing the thetas in the cost function. We are adding epsilon to every value of the theta, theta 1, theta 2. Or in the normal words, you can think for every parameter w1 and w2, we are adding the epsilon. This is the, by adding to every parameter epsilon, we have calculated the cost function, that is j. You can call it as a j1. And by subtracting from every parameter epsilon, we have calculated the cost function. Now we are calling this as a j2. And we are subtracting j1 minus j2. We are dividing it by 2 epsilon. This is giving the differentiation of the cost function with respect to the theta. Now we are checking this with respect to, already we calculated the differentiation. So already calculated differentiation we are calling as d theta, and now the differentiation we are calculated we are calling as a d theta approx. And remember, this is only for one training sample, but for m training samples we will have a matrix, d theta matrix and d theta approx matrix. Now we want to check whether the d theta approx is equal to d theta or not. If it is a single element, we can check, but these two are matrices. How can we check whether the elements in these two matrices are equal or not? How can we check the error? Now there is a concept in which we are using the same L2 normalization. We are subtracting the two matrices d theta approx and d theta. Because these two matrices are having the same size, matrix subtraction is possible. After finding the subtraction, we are using the normalization, means we are adding the squares of each elements in the matrices. Why we are adding the squares? Because sometimes the error may be the negative, sometimes error may be the positive. That's why we are adding the squares of individual elements. After subtracting, we are adding the squares. So after adding the squares, we are taking the square root. This is what we are calling as normalization. After we are taking the square terms, we are using the square root. Similarly, at the denominator side, we are taking the square root of individual elements squares for d theta approx and d theta. If the result is 10 in the range of 10 to the power minus 7, then it's great. The gradient descent we are using to find the cost function is properly finding the gradient. You can proceed. But if its value is greater than 10 power minus 3, then there is a fault. You have to check where the fault is. Now, if we are finding that fault, first we have to check what are the values that are mismatching. In these d theta and approx and d theta, all values may not mismatch. Only some particular values may mismatch. Now we can check which particular layers values are mismatching. We can go to that layer and we can change the parameters either by increasing the number of activation units or by changing some parameters regarding the W, which are controlling the activation units of that particular layer. That can be done. And some points we have to remember: we should not apply this gradient checking method for the training set. We should only apply at the stage of debugging, means for the crash validation set only. Why we are not applying at the training set? If we apply there also, we can find whether the gradient descent is working properly or not. We can find the training set error also properly. Yes, of course, but we are giving a huge amount of training data. The numerical computation is very slow. If you try to compute numerically the training set, then it takes a huge amount of time. Why we are going for numerical approach? Remember the purpose: only to check whether the gradient descent is calculating in the gradient descent, we are using proper gradients or not. We are checking the gradients. For the checking purpose, only at the crash validation time you can use this method. In the crash validation time, if you use, you can save a lot of amount of time, and computationally your learning algorithm will be efficient. If you apply this at the training time, then it consumes a lot of amount of time. So first point we are saying, do not ever try to use this gradient checking at the training time. Use only for the cross validation set. And the second point, remember to use the regularization if you are already applying. If you are applying L2 regularization, then use the regularization term even for the numerical computation also. Do not forget it. But if you are using the dropout regularization, don't try to implement the dropout regularization when we are using the numerical computation. It will give the false results or some errors. So if you are using the dropout regularization, immediately make the keep probability as 1.0. This is a very important point you have to remember if you are using dropout regularization. And sometimes even if you have included the regularization term, and even if you kept the keep probability as 1.0, if you feel the gradient checking and also you have checked that at a particular layer some error is coming, you have changed some parameters, and there is a then still you want to after applying all these methods, if still the gradient you have found by using the numerical computation is not matching with the gradient we have found by using the calculus or using the previous method, then you can apply the random initialization after some training. Means after some iterations, you can again initialize the W with the random initialization, then you can proceed. This is the final option. You have to choose this option only if the previous options are not at all worked out. This is how we use the gradient checking for the purpose of only to check whether our gradient descent algorithm is properly finding our parameters or not. For the checking purpose only, this numerical computation is useful. This we are using as a secondary option. We are not using as a straight option, because to find the numerical compute by using differentiation by numerical computation itself takes a huge amount of time. That's why we are only using to check whether already the gradient we have found is proper or not.